Hello, my name is Zhongmo Chao, and I'm going to tell you about our work on ionic liquid regulated silver filament formation for neuromorphic applications. People have been using the conductance of different electronic devices to emulate the logic states in neuromorphic computing. For example, binary state CPRAM. Even though they only have two states, because of a simple structure, for example, multiple CPRAMs can be connected either in series or in parallel to achieve different conductance states as demonstrated on the right. But as we can see, to achieve finer conductance change, more devices are required, making it challenging for binary state CPRAM to achieve analog conductance change energy efficiently, which is required for neuromorphic computing. For this specific reason, lots of efforts have been made to make CPRAM to have multiple states. People usually do so by engineering dielectric material to guide the metal filament growth towards a more controlled manner. Even though some progress has been made, the control over filament conductance is limited. For example, as shown in the figure, when using a formation pulse or a dissolution pulse to grow or dissolve the filament, the current change is nonlinear and asymmetric. This nonlinearity is critical as it will degrade neural network accuracy. For example, as shown in the figure on the right, when the nonlinearity magnitude increases from 1 to 2, the accuracy drops from 90% to 20%. To address this challenge, we come up with an electrolyte system consisting of an UV cross-linkable polymer mixed with an ionic liquid. PECTA has very similar structure with the commonly used PEO electrolyte, except it has two end groups which can be UV cross-linked to improve electrolyte mechanical strength. BMIMPF6 is room temperature ionic liquid usually added in battery to improve ion mobility. We use the conducting AFM-based system to study silver filament formation and dissolution between an AFM tip and the bottom silver electrode. Here, the conducting AFM tip and the silver layer represent two electrodes. Because AFM tip operates as a mobile top electrode, it enables us to direct write filament at pre-selected locations. For example, with the AFM setup, we can collect the data from hundreds of formation and dissolution events at different locations using a customized script, making our results more representative of our system. We first studied the impact of formation bias on silver filament formation kinetics. Owing to this direct write functionality, at each bias ranging from 0.7 to 3.0 volt, more than 500 formation events have been collected, and all their formation times are plotted in this figure. Before digging into the data, you would probably think, when increasing the bias, we're increasing the driving force for basic everything around filament formation, electrochemistry, ion migration, so of course the filament formation will be faster. Well, as it turns out, interestingly, we observe a non-monotonic trend of formation time versus bias. To be more specific, we find formation time starts to increase when bias is approaching 2.0 volt before it decreases again, forming a peak of formation time at 2.0 volt. In fact, for all three systems ranging from 30 to 48% of ionic liquid, we observed a similar peak at around 2.0 volt, and it seems the peak intensity increases with ionic liquid composition. Not only the longer formation time, when we look at the filament structure formed at where the peak appears using SEM, they can be easily identified from others because they have the most obvious lateral structures. At this point, we are not sure what is happening near the 2.0 volt, but we are certain whatever the cause, it is highly sensitive to bias. Because of this thinking logic, we started to pay more attention to ionic liquid. We know ionic liquid is consisting of charged ions when they are presenting in the electrolyte. Using this parallel plate structure as an example, after applying electric field pointing up, in response to electric field, ions with different charges will separate and migrate towards different electrodes. Once they aggregate near the interface with both electrodes, they are forming two electrode double layers. Now, because the charged ions are separated, they can induce a virtual internal electric field pointing down, contradicting the external electric field. This means once EDL forms, it will screen the field and slow ion transport in the bulk electrolyte. One signature of EDL formation is a charging current signal which can be detected by AFM. To study the EDL formation in our system, we tested a set of biases ranging from 0.7 to 3.0 volt. At each bias, 3 measurements were conducted at different locations. The current versus time data at each measurement were then plotted using different colors. As shown in the figure, noticeable current signal can only be observed when bias is approaching 2.1 volt, right at the bias where the peak filament formation time appears. Because we know once EDL forms, it will screen the field, and we suspect the screening effect is slowing filament formation kinetics. So we came out with a new contrast experiment. This time, we allowed the AFM to discharge the previous form EDL before starting a filament formation event. We have compared the formation times at different bias with and without discharging EDL. As we can see in the figure on the right, by discharging the EDL, formation time is decreased at all biases we tested. This trend is especially obvious at the peak formation bias 2.1 volt. Under the new procedure, the formation time is decreased by 20 times, meaning EDL has strongest impact on the formation kinetic at this bias. In contrast, EDL has relatively smaller impact on formation bias at both ends of this bias range, either at 0.7 volt or at 3.0 volt. Also, we found two different current versus time patterns during filament formation. For the type on the left, we noticed an abrupt transition from zero current to a high current, while for the type on the right, the transition is more slowly and more gradual. We distinguish these two types as abrupt type and gradual type. In fact, abrupt type is commonly reported in literature, and it is considered as a typical matter of filament formation dynamics. In contrast, the gradual type is quite unique to our system. When plotting the distribution of growth types against formation bias, we notice gradual type is mostly identified at 1.8 volt, a bias right before the strongest EDL screening, while at all other biases, the abrupt type is dominating. Because gradual type is mostly observed at 1.8 volt, we propose the degree of EDL screening at 1.8 volt is just enough to turn its formation from abrupt to gradual. For the gradual growth type, we demonstrate here that we can tune its conductance states to achieve a set of intermediate states between the high and low, distinguishing itself from abrupt growth type. So we are trying to find out whether the gradual growth type filament can help achieve the analog requirement for neuromorphic computing. Our previous results are collected using a mobile conductor AFM that lacks scalability for neuromorphic applications. Therefore, in our recent work, we present lithographically patterned devices of which electrical characterization are conducted on probe station. The location and dimension of bought and silver electrodes were directly patterned using photolithography. Silver electrode dimension was set to 20 by 20 micron. Gold contact pads were also patterned near the edges. The electrical connection between each silver electrode and gold contact pad was made by thin silver extension arm. After device fabrication, we spin-coated the polymer ionic electrolyte and UV cross-linked the film. Conductor AFM is then used to direct write filament at the region right above each silver electrode. After filament formation on AFM, we then deposit a top gold electrode to cap the electrolyte that contains filaments and make the sample ready for probe station measurement. If we forget the filament form for a moment and draw a cross-section view along cut line 3, it will look like multiple MIM structures packed horizontally with a common top gold electrode. During the initial filament formation using conductor AFM, we deliberately overgrew the filament to improve its electrical contact with top gold electrode, which is crucial for probe station measurement. Although we notice filaments tend to disconnect during sample processing, but they can be reconnected relatively easy using an active bias. Once reconnection was made using constant negative 1.2 volt, we then switched negative 1.2 volt pulse to further grow the filament. As shown in the figure on the right, the conductance of filament was measured using negative 0.05 volt read bias. From cycle 31 to cycle 250, we can see a linear correspondence between read conductance versus write pulses, changing the conductance from 247 to 260 microsiemens. After 250 cycles of negative 1.2 volt pulse, we then switch to positive 0.2 volt pulse to dissolve the filament, and from cycle 251 to 470, the conductance decreases linearly. Although we are still trying to get a better sense of what is going on at both ends of the cycle numbers, within the highlighted region, we have demonstrated gradual formation and dissolution using bias pulse, and more importantly, we show a linear and symmetric conductance change. In conclusion, we uncovered a new control mechanism to regulate filament formation dynamics using ionic liquid electrodouble layer. We have no reason to believe such control mechanism is unique to our system, and therefore could be exploited for other material systems or for different applications. Also, we have demonstrated linear and symmetric modulation of filament conductance using bias pulse on lithographically patterned devices, making our system promising for neuromorphic applications. I would like to thank my collaborators both at the University of Pittsburgh and the University of Notre Dame. I'm also very grateful for the support from DAPA and PPG Graduate Student Fellowship. I am currently looking for a postdoc opportunity in related research area. It would be greatly appreciated if you can share the information to potential interested employers. Thank you for your attention, and I'm happy to answer any questions you may have.